Hey guys, so we left off last week discussing this slide here in the chapter 3 notes, and the idea here is that if you have 1 gram of water, it's going to take 4.184 joules to increase the temperature by 1 degree. So that's the specific heat of water. That's where this number comes from. So joules per gram and degree Celsius. So this is the specific heat for water. That again is just a measurement of how much energy water can absorb when you consider mass and how much temperature change happens. So if our temperature change was 2 degrees instead of 1, it's that same number, but we're going to multiply by 2 degrees, right? Because that's going to cancel. We still have 1 gram, right? So we're going to cancel grams by doing that. And so, this basically mathematically boils down to 2 times 4.184. So you're going to get 8.368 joules of energy to heat up 1 gram by 2 degrees instead of by 1. So, it's just double. If I wanted to take 2 grams, it's still the same specific heat. And I want to increase it by 1 degree, so we're going to say 1 degree, right? You're going to get the same answer numerically. It's still 8.368 joules. The Celsius cancels here, the grams cancel here. So this is just dimensional analysis where we're canceling grams and degrees Celsius to find out how much energy is needed. Joules is energy. So it doesn't matter whether it's 2 degrees change or whether it's 2 grams of material. The amount of energy required is the same. So that's interesting. And then the last question here is how about if you had 2 grams, still the same specific heat, so we can put that down. And I want to heat it up by 2 degrees, right? So again, it's dimensional analysis. So everything is multiplying in order to cancel everything except for joules. So this time we get 2 times 4.184 times 2 again is 16.736, which if I'm paying attention to significant figures, wouldn't have that many, but we'll just simplify for the purposes of this slide here. Okay, so this leads us to the discovery of an important equation. Okay, so the variables are defined here for you. Q is heat, so this is going to be measured in joules or calories. Those are the 2 units of energy we've talked about, joules or calories, or some derivative of that, like kilojoules or kilocalories, right? But those are the base units. M is mass, so this is going to be in grams. Okay. S is that specific heat that we were talking about. Like for water, it's 4.184. Every substance has its own specific heat. All right, but the unit for S is joules per gram degree C. Okay, so that's our S here. And then the last term is delta T. So delta in science means change. Okay, so this little triangle means the change in temperature. So a change in temperature is the final temperature minus the initial. Okay, so when the last slide here, let me go back. When the last slide says that we are changing the temperature by 1 degree Celsius, that's a delta T. So by means that you've subtracted final minus initial already. If it says from something to something else, that means I have to do the subtraction, right? So from and to are an indication that you have to subtract. Just to be clear, the from is whatever's after the from is going to be the initial temperature, and whatever's after the to is going to be your final. So they're kind of going to be worded backwards from how you're going to do the math. So watch out for that. Okay. So this formula, there it is, allows us to calculate how much heat is going to be used depending on how much mass of substance, whatever heat capacity it has, and how much temperature change is occurring. So S for water, again, this is just specific to water, is 4.184 joules per gram degree C. So if I'm working with water, I can always use that as a constant to fill in here. And then if I just know the mass and how much the temperature changed, I can find energy. Okay. Or sometimes maybe we know the temperature change and how much energy, but we don't know the mass. So there might be different types of questions you can get that are going to use this equation. Okay, so here's one example. It says methane is a highly energetic fuel source. We call it natural gas. That's what you get from National Grid if you can get natural gas from them. It burns and produces 802.5 kilojoules of heat. We want to know how many calories that is. Oh, so this is going to be a conversion. We're going from kilojoules into calories. So I don't even need the equation for that. All I need is the relationship between kilojoules and calories. I remember from our discussion last week that there's 4.184 joules equal to 1 calorie. You'll notice this is a capital C, the scientific version, okay, not the kind you would find on the nutritional labels, okay. If this was about nutritional calories, it would say nutritional here, and it doesn't. So that's a context clue as well. I can translate this into conversion factor just by turning it into a fraction. So there's 4.184 joules for every 1 calorie. Or I can also say that 1 calorie for every 4.184 joules. These are just facts, okay? So these are the relationship between joules and calories. Now, kilojoules is not the same thing as joules, so I probably first need to go to joules and then to calories. There's not a direct, I don't know the direct relationship here. So, kilo is the big one. So I have 1 kilojoule for every 1,000 joules. Okay, so there's a factor there. So now that I've got some facts written down, I can actually start with what I'm given. And this is all dimensional analysis because we're converting from one unit to another. I want to get rid of kilojoules here, so I have to put it on the bottom. And our fact up here says there's one of those for every 1,000 joules. Okay, so that gets kilojoules canceled. The next step is going to be to cancel joules and to get it into calories. I'm going to use, well, see, this one won't work because joules is on top here, so that's not going to cancel. I'm going to use this one because it will cancel. So we put 4.184 joules on the bottom and 1 calorie on top. Okay, this way the joules that are on top here are going to cancel and we'll have calories left at the end. So I know I've done it correctly because my unit is right. So then I just got to plug it in the calculator. So it's going to go 802.5 times 1,000 because the 1,000 is on the top, and then divided by 4.184 because it's on the bottom. And the answer that the calculator gives me is 191,802. And that's going to be calories because we canceled everything else. Now I want to check my sig figs. It's always going to be based on the original data I start with. This 802.5 has 4 significant digits. This 0 is significant because it's trapped. So all these numbers count. So I need to have 4 digits in my answer. So we go 1, 2, 3, 4. That's the last actual number I can keep. The rest of these are going to be replaced by zeros where that arrow is. So it's going to go 191,800 calories. And that is the correct answer. All right, so I want you to do the same thing, but this is for a different calculation. So go ahead and answer this one, and I'll grade this when you turn in your notes, which again are due at the beginning of class this week. Okay, so this one, let's start by assigning variables. How much heat is needed? So heat is Q from that equation we had earlier. Heat is Q, lowercase q. So we're trying to find Q. It is needed to raise the temperature of 140 grams. 140 grams, that's going to be a mass, okay, because grams is a mass. So 140 grams of water by 15 degrees. So when it says by 15 degrees, that means that's the delta T. So here's what I know. I know the mass is 140 grams. I know that I'm looking for Q. I know that the delta T is 15.0 degrees Celsius. Oh, and I also know that it's water. It's water. It says it's water. So I know that the S of water is that funny 4.184 joules per gram degrees C. Our equation, when it's not a conversion, it's going to be the equation. So those are our two choices. It's either dimensional analysis or an algebraic equation. In this case, we have too many variables for it to just be converting something. So we've got to plug it in, right? And then we're trying to find Q. So all I do is plug everything in. So M is 140 grams. C and S are the same thing. Okay, so your textbook bounces back and forth, and different websites will use both of them. They mean the same thing though, either way. Okay, so that's the 4.184. And that depends on what material it is. I knew to use that one because it says water up here. Woo, that's a long line. And then the change in temperature was by 15 degrees, so it increased by 15 degrees. So that's all I have to do. It's just setting it all up. Now, before we plug anything into the calculator, we want to make sure that we get the right unit. So we should expect joules or calories because that's what heat is. So the grams are going to cancel. And also the Celsius cancels because there's one on top and one on bottom. And that just leaves us with joules, which is an energy. So that's what we expect to have. So we're going to go 140 times 4.184 times 15, and it's going to give me 8786.4. And I know that's joules because it's the only unit that's left. Now I have to go back to my original data and figure out how many significant figures to keep. This number, 140, has just 2. There's no decimal, so this one is not a sig fig. So it's just the 1 and the 4. The 15 degrees is 3. That 0 is significant because it's after a number and a decimal place. So, but if I have 2 in 140, that means I only get to keep 2 in my answer. So we go 8. This 7 is going to get rounded because it has an 8 after it. So it's going to be 88 and then 2 zeros, joules. That's my final answer. All right, so this one is a very similar process. I want you to write down what you know, assign your variables, right? And so again, the equation, you'll always be given this, but you know, it's in your notes. The equation is MC delta T or MS delta T. The C and the S are the same thing. So just assign what you know. Take a second, pause the video and do that. Okay, I'm going to assume that you did that. We're going to break it down though. So 110 grams is going to be mass. Mass is M. I don't know what the material is, so I don't know what the S is. It says it's an unknown material. It's not water, so I don't know what the S is. What is the specific heat? Oh, that's the S. Okay, so good. We're looking for an S. If 1402 joules is needed. Oh, Q is joules, so we're going to say heat. So Q can either be calories or joules. It's heat. So in this case, we get joules. And then, of course, the last thing is 2 temperatures. The temperature from 24.6, so that's what we labeled as the initial temperature. It's like where it starts from. I'm going from work to my home. That means that I start at MV and I go home at the end, right? So from is the initial. The 2 is the final, and it says 85.2 degrees. So I can combine these together. I go final minus initial in order to figure out the temperature change. So in this case, 85.2 degrees Celsius minus 24.6 degrees Celsius. So we get 60.6 degrees. And I want to just remind you that when you're doing adding and subtracting, the significant figures, the place value is what matters. We have tenths place, so my answer needs a tenths place. So delta T is 60.6. Okay, so now I can write down everything I know. For the Q, let's see, we're trying to find S. We're trying to get S by itself. So we can rearrange this equation. Okay, so there's the equation that we're starting with. If I want to get S by itself, I have to undo everything else. So I got to get rid of the M by dividing both sides by M. Okay, so that gets us to this place. Okay, if I still want to get the S all by itself, so the next thing I'll do is divide by delta T on both sides. Okay, so we're going to get Q on top, delta T and M are both on the bottom. This is multiplied together. And it's going to equal S, which is what we wanted to get to, is the S. So I can use this formula like that to figure out S. All right, so S is going to be equal to Q. We said Q is 1402 joules. Let's see, delta T, we have 60.6. And mass, we said, was 110. So now this is going to come out with the correct units, joules per gram degree Celsius. So I know that I've set up my math correctly. Don't forget that the bottom is multiplied together, so you might want to do that as a separate step. So 60.6 times 110 would be on the bottom. And then 1402 divided by that. So I got 0.210321. We're going to look at our data and we see 3 significant figures, 4 here and 2 here. So we're going to go with 2. So 0.21 joules per gram degrees C. That's our final answer. All right, so sometimes we have to use density as a conversion factor. So this is an example of that. We have some experimental data about measuring ore. Okay. In order to use density, we have to measure it, right? So here we have an initial volume and a final volume. So to get our change in volume, we just subtract final minus initial. And so we find out that the gold occupied 3.45 milliliters. And similarly, we're going to have to subtract to get the mass, right? So we just want to have the mass of the gold. We're going to take final, which is full, minus our initial weight, which was the empty weight. So 36.2 is what my calculator says. That's going to be grams. Now, when I'm subtracting, I have to pay attention to place values. So there's a tens and a hundreds place. My calculator says the answer is just a tens place, but I know that I have to maintain the right significant figures here. So I have to put a 0. So now we have the mass and the volume. So in order to get density, we just divide them. So 10.49 is the density of this material. Now this, we have 4 significant figures on top and 3 on the bottom from our volume. So I'm actually going to have to, record that as 10.5 because we only had 3 significant digits to use. Okay, so 10.5 grams per milliliter happens to be the density of this material. Now, I'm probably going to use that here on this problem because this is about silver ore also, so we can just jot that down as a fact that we have, right? The density is equal to that. I have a volume of 4.21 milliliters of silver, but there's no volume in this equation. So I'm guessing I'm going to use the density and the volume together, right? So we're multiplying. This is, again, just dimensional analysis. So we're multiplying in order to cancel the milliliters and get it into grams. My calculator says 44.205. I only get 3 of those numbers, so 44.2 milliliters. Nope, sorry, wait. We canceled milliliters. Now it's just grams. Okay, so now we know the mass. That's mass comes from there. Okay, that's M. We are heating it from room temperature, so that's going to be my initial. So 22.0 degrees. Up to 950, so our final temperature is going to be really hot. Oh, there's no point there. So the change in temperature is going to be the final temperature minus what I started at. So 928 degrees Celsius is our change. That got very hot. All right, so that gives us delta T. So I got M, I got delta T. Oh, and it says if the heat capacity of silver is 0.23 grams. So that's our variable. So now I have everything I need in order to plug it into the equation, right? So we're trying to find heat. The mass is 44.2 grams, so that's M, times delta T, sorry, times S times delta T. So our delta T was 928 degrees Celsius. So the calculator says that my answer is 9434.05. I only have 3 significant figures because of my mass and 2 because of our specific heat. The 0 in the front doesn't count. So that means I can only keep 2 numbers. So 9434.05 is what it says. So I'm just going to turn those last 2 digits into zeros. We don't just drop them, okay? So that's the difference between $9,400 and $94. So they still have to have the same magnitude. We just are making sure to communicate precision correctly by having the right number of significant figures. All right, so you might be wondering why or how we measure heat, and you're going to get to do this in the lab actually, so that's a good opportunity. We're going to use the coffee cup calorimeters here, which are just 2 coffee cups stacked together with a lid on them and a thermometer to measure the temperature of the contents inside. This is a great way of isolating our reaction so that no heat is exchanged and all of the liquid is trapped. On the other hand, we have something over here. This is just cleverly called coffee cup calorimetry. It doesn't have a fancy name over here on the right. Bomb calorimetry is done in a vessel that is pressurized. That's why it's called a bomb. Okay, and this is often used to measure the amount of energy and calories for food. That's how they figure out how many calories your snack has. So here, the way it works is your sample is sitting in a little cup, an ignition cup in here, and little electrodes go into it. And then this cup is surrounded by a ceramic outer chamber, okay? This is sitting in a pool of water, so you fill this up with water because water will circulate and surround everything and make sure that it captures all of the heat that's being made by this experiment. So the idea here is that you can measure the temperature of the water, and as long as you're mixing it really well, the temperature of the water anywhere in the flask should be the same as the temperature of the reaction. All right, so we have a stirring thingy, we have the electrodes to light it on fire so it'll burn, and when it burns, it's going to heat up this container that it's in, and then it's going to heat up the water, and we're going to be able to measure the temperature change. So that's bomb calorimetry. It is constant volume, meaning the volume is stable. Okay, whereas the coffee cup calorimetry is what we call constant pressure. Okay, so as the left-hand example heats up, it's going to be under increasing amounts of pressure, whereas the coffee cup calorimeters are at atmospheric pressure. So that's not going to change dramatically during. Okay, so those are the 2 types of calorimetry. We're only going to do the constant pressure calorimetry, that's this one, in the lab. But you know, we've had people do undergraduate experiments about comparing freezer food to homemade food to see if the calories are different. So that's the kind of experiment you could use the bomb calorimeter for. Calorimetry literally means, so calorie means energy, right? Mostly in the form of heat. And metry means measuring, like metric. So we're literally measuring the amount of heat using these methods. And they're funny setups because we need to make sure the heat stays in a measurable place. You wouldn't just put it in the air because air will absorb the heat and it changes it. It's really hard to measure. So here we're trying to create isolated systems where everything is trapped. Okay, so the formula from chapter 10 is this one. The only other kind of math question you're going to get is going to be like relating substances to each other. So here's some unit conversion that we might run into. So 1 scientific calorie equals 1,000 kcal, which is the same thing as saying 1,000 nutritional calories. Okay, so those are some facts, some conversions that are helpful to have. Now, if I take some hot water and I dump it into the cold water, obviously the cold water is going to warm up and the hot water cools down, right? So the hot water temp decreases, it comes closer to the temperature of the cold water, and the cold water temp increases. So they kind of almost like average out. That's because when two objects touch each other, their heat is exchanged until they're equal. Okay, so it's like a wife with cold feet puts her feet against her husband's back because it's warm. So his back is going to get cold, her feet are going to get warm. Eventually they end up at a temperature that's kind of in the middle ground. Okay, so in a similar way, if I take really hot metal and I dump it into cold water, the temperature of the metal is going to cool and the water is going to heat up. I can actually measure how much it heats up, so that's kind of our goal. Whoops, wrong way. All right, so you can write some expressions. M here means metal. So the top one here is all about the metal. The mass of the metal times the heat capacity of the metal times the change of temperature of the metal will give us the Q of the metal. Now, Q of the metal is a little bit difficult because it's pretty hard to measure temperature of a solid object. Certainly our laboratory thermometers wouldn't do that very well. So instead, we're going to use a relationship between water, which is surrounding the solid material, which is hard to measure the temperature of. It's easy to measure the temperature of water, so that's why we do this. All right, so you can write another statement for water where the Q, so when we say W here, we're talking about water. The heat of the water is equal to the mass of the water times the heat capacity of water. And again, heat capacity of water is that 4.184 joules per gram degrees C. And then of course the temperature change of the water, which you would have to measure. So we're going to have this system where we have our coffee cup. Here's our awesome drawing of a coffee cup. And inside the coffee cup is going to be a little metal object that we heated up. So that's our hot metal. And because it's going to be touching the water inside the cup, it is going to change the temperature of the water, and we can measure that. Okay, which would allow us to calculate how much heat was involved in the process. So basically we're going to find QW. That's our goal. Once we do, we can use this relationship. If I know QW, it's going to be the same value of QM, but QM will be negative. All right, so you can take these two formulas and smush them into one giant formula if you want to. This is a great way of thinking about it. The mass of the metal times the heat capacity of the metal times the temperature change of the metal is equal but opposite. So opposite because it says minus. So equal but opposite of the mass of the water times heat capacity of water times temperature change of water. Okay, so you can use this one equation if you want to, or you can solve for the Q's and remember this one. Either way works just fine. I don't care which way you go. All right, so our last example that we're going to do together is a steel sword a blacksmith is making. So it's a lot of words, we're going to break it down. So a blacksmith heats up a steel sword weighing 1.4 kilograms. So 1.4 kilograms is a mass. So far I've only been using grams, so I'm going to guess that I probably need to convert this where I get rid of grams. Sorry, where I try to get to grams by getting rid of kilograms. So I put kg on the bottom. So that's going to give us 1,400 grams of stuff. Oh, and it says that it's glowing red hot. So its temperature when it's glowing, so that's kind of like the beginning of our problem here, is 820 degrees Celsius. Now this is the metal we're talking about, so I'm going to put that. I'm going to put the initial temperature of the metal and the mass of the metal is here. And then he plunges the sword into 20 liters of water. Oh, they give me a density. Okay, so I don't think I need volume here. So we're going to just take the volume and turn it into mass. Okay, so it says 1.00 grams for every 1 milliliter. Well, milliliters and liters don't cancel, so I got to put in a relationship for those where I want to put milliliters on the top. So there's 1,000 milli, like 1,000 millennium for every 1 liter. So this will be milliliters cancels. The liters is going to cancel. And so at the end, we end up finding out how many grams of water were present. So it just boils down to 20 times 1 times 1,000, which is a lot. So it's 20,000 grams. Because grams is the only thing that's left. It also tells us that the water is 20 degrees Celsius. I think that's my initial temperature of the water, which is 20 degrees. The sword is allowed to sit in the water until it has cooled to the temperature of the water. The final temperature, oh, so that's TF, is 26.5 degrees Celsius. Now, it's important to understand that this is the temperature of the water and the metal because they're both touching each other. So the temperatures are going to become equal. So if I measure the temperature of the water, it's the same thing as the temperature of the metal. Okay, so the final temperature there is 26.5. So I can calculate a delta T for the metal, let's say, right? It starts at 820 and it ends up at 26.5. So that's going to be final minus initial. So our answer here is negative 793.5. Okay, our temperature change for the water is going to be the final state. These are the same again because the two objects are touching. And the initial state. Okay, so now I have a delta T for the water and for the metal. I know the mass of the metal. I don't know heat capacity of the metal. Oh, but I do know the heat capacity of water because that's a constant. So I think I can calculate the heat for the water part and use that. So Q of the water is going to equal to the mass of the water, which we said was 1,400 grams, times the heat capacity, times the change in temperature of the water. So that goes up 6.5 degrees. Okay, so 6.5 times 4.184 times 1,400 equals negative 5851.1. We have two significant figures, it looks like. So we're going to write 5900. And Celsius cancels, grams cancel, so I'm left with just joules. Okay, so that's the heat of the water that was absorbed by the water, okay? It's going to be equal but opposite to the metal, right? So if we got 5,900 joules for the right-hand side, the left has to be negative 5,900 joules. So that's the answer. That's the heat anyway. That's not really an answer, but it helps us get there. So that's the heat of the metal, and it equals this many. Okay, so our last step is going to be to take that heat and find heat capacity. So you can rearrange the equation first, or you can plug in and then rearrange. I don't care which one you do. I'm going to divide both sides by m and by t, so I get S on one side and m delta t on the other one. So we have that. Okay, so now all I have to do is plug it in. So Q equals that negative 5,900 we saw. M is the mass of the metal. Oh, you know what? I think we used the wrong mass down here. This is supposed to be mass of the metal, or we used mass of the metal. It should have been mass of the water. Do we know that? We do, 20,000 grams. Whew, that was a close call. So instead of that answer, we get calculator says 543920, but I can't keep all of those digits because I only have 2 significant figures in my temperature. So it's going to be, whoops, 54123 joules. Okay, so that's actually our QW. And so our QM is going to be the negative of that. So QM is negative 540000. So I can't erase that one, but let's just ignore it. So negative 54123 joules. On the bottom we have grams. That's where your 14,000 comes in. So we need to be very careful about where we assign things, whether it's a metal or the water. And the change in temperature is going to be this negative 793.5. Which is good because it turns out if you have a negative and you divide by another negative, it becomes positive. So we get that 5,400 number. I'm going to divide it by 14,000 and also divide it by negative 793.5. And we get 0.04896. So the S is 0.04. So you only got 2 numbers, so I'm going to round that one. And the units are joules per gram degree C. Okay, so that's it for this lecture notes. I want to write one more problem for you to do. This is going to be graded on your notes. So here's another problem. I'm going to write this down while the video is paused. Just one. Okay, so here's our problem here. Oh, where did that whiteboard go? Oh no. Okay, so here's our question, all right? So we have some data here. There's actually 3 different parts to this question, so I want you to show me your work. If you have to do any conversions, you need to use dimensional analysis, but otherwise you can refer to our heat equation, okay? And make sure that you label everything really clearly so I can follow your work. You can do this in your notes or attach it to your notes, and I will grade them this week. That's going to be it for today, so good luck. And as usual, if you have any questions, feel free to email me.